Hello everyone, my name is Zhu Zhengxiang. I'm delighted to have the opportunity of making this presentation for the conference CSCC 2020. The subject of my presentation is revising the security protocols against network attacks based on the event B. After a brief introduction of the background and content of my work, I will introduce the modeling of network attacks and the modeling of protocol improvement process respectively. Network everywhere. Internet, mobile payment, Internet of Things, 5G all use security protocol. However, these protocols are not always secure, and logical vulnerabilities often arise in complex operating environments. So various manufacturers issued patches to fix the vulnerabilities, but the practicability and availability of the patch was not guaranteed. For example, Microsoft patched the SMB Ghost vulnerability in March this year, but the patch was exposed in June with similar vulnerabilities. In this context, this paper proposes a generic framework based on the Event B method and Rodan platform to guide the revising of a security protocol so that the unknown successful attack can no longer take place upon the revised protocol. In this framework, we will model the protocol and attack behavior first, then the process of protocol improvement, namely patch, is successfully established in the model and the rationality of the improvement is verified. Before I introduce our work formally, I will give a brief introduction to the Event B method. The Event B is a modeling method proposed by Professor Abriel. You can look at it in detail in the book showed on the PowerPoint. The Event B model can generally be composed of machine and context components, which define the dynamic and static parts of the model respectively. Variable types, constants, axioms, and theorems are defined in context. Variables, invariants that represent the nature of the system, theorems, events, and so on are defined in machine. Events are the most important part of the Event B model that describes the behavior of the system. You can set local parameters, conditions for event execution, and actions to be performed after the event is triggered in EVNet. If modeling is correct, the proof obligation generated by invariants of abstract models should be proved to be in the current models and the concreter models. The Event B development approach is based on the refinement theory. There are three benefits to adopting the Event B approach. First, Event B method models from an abstract model, which is relatively easy to model. Second, each behavior of the protocol and attack is described by events in the model, which is modularized development. Third, refinement theory can ensure that the development results meet the agreed nature. Here's a formal introduction to our work, starting with some basic definitions. Because our work is to model the behavior of the protocol and the attack together, we need to define the agents in the model. Protocol agents that represent honest agents, and attackers that include renegade agents and the third attack party. We then classify the events in the model according to their handlers. Protocol event is the event performed by a protocol agent that describes the normal operations of a protocol. Attack event is the event performed by an attacker that describes the process in which the protocol was attacked. Public event is the event that has no explicit executor, or the event describes the changes in the state of the modeling. So how are these three types of events represented in the model? We added three access properties for variables in the machine part. As shown in the picture, we make the following rules. Protocol events can read and write protocol variables and public variables, without any access to attack variables. Attack events can read and write attack variables and public variables, without any access to protocol variables. Public events can only read and write public variables. By modeling according to this rule, we can clearly distinguish between the types of events. Based on the definitions and rules given above, we can build an Event B model. For example, Model 1 consists of 3 protocol events and 3 attack events, where event S represents the successful attack. There are at least 2 event execution paths in the Model 1, normal protocol running path P1, P2, P3, and successful attack path, P1, A1, P2, P3, A2, and AS. The event AS that indicates successful attack in the successful attack path is finally triggered. A model like this, in which there is at least one successful attack path, is called the successful attack model. From the above definitions and refinement theory, we infer such rules as, if model A is attack success model and model B is the refinement model of A, then B is also the attack success model. Correspondingly, there is a protocol model in our framework which indicates that there is no security vulnerability. We give the definition: if there is not an event execution path in the model that the path is successful attack path, this model is called the attack unsuccess model. After we have established an attack unsuccess model that truly reflects the attacked protocol, what we need to do is to develop patches or implement patches on this model, as shown in the PowerPoint. After P3.1 is obtained by refining P3, the model 2 is obtained, which means that the event as cannot be triggered, and model 2 is an attack unsuccess model. To sum up, our modeling method can be summarized as follows. In the first step, the initial abstract model represents the attack success model. The second step is to add protocol and attack behavior details gradually by refining the model. The third step is to get the concrete model which can reflect the real protocol operation process and attack process. In step 4, we need to separate the concrete model, because we improve the protocol part separately, not the attack part. In step 5, we model the patch or improve the protocol in the model. The separation rule of the model are shown in the small figure on the right. Protocol events and public events are protocol part, the attack events belong to the attack part. Now, moving on to the third part of the presentation, we'll look at how revisions are built into the model and how these revisions can be verified. The first revision method, which has shown in the previous flowchart, is refining the protocol part. First, we separate the concrete model, and then refine the protocol part separately, so that the nature of the protocol part can be guaranteed. Then we manually construct the new attack part according to the original attack part and the improvement process. If the new protocol part and the attack part recombine to obtain a new model, and this model is attack unsuccess model, then our revision is reasonable. The former does not change the original nature of the protocol and is typically used to indicate that a defense mechanism is added to be patched. However, the unreasonable mechanism of the protocol is often the direct cause of the vulnerability. At this time we need to change the original nature of the protocol. The first revision method is obviously not suitable. So, we put forward a new revision method accord with the refinement theory to change wrong protocol properties. Through refining the protocol part of the abstract model again, the problem of protocol mechanism has not been added to the system, and we set up a new, correct protocol mechanism. Because the protocol mechanism is changed and no other new modeling elements are added, the attack part generally does not change. Similarly, if the new protocol part and the old attack part recombine to obtain a new model, and this model is attack unsuccess model, then our revision is reasonable. Because the protocol mechanism is changed and no other new modeling elements are added, the attack part generally does not change. Similarly, if the new protocol part and the old attack part recombine to obtain a new model, and this model is attack unsuccess model, then our revision is reasonable. After we implement the protocol revision in the model, we need to verify the reasonableness of the revision, and we provide two approaches. The first is through checking the refinement relationship between models. According to the previous inference and the definition of attack unsuccess model, we can get inference 2 if model B is an attack unsuccess model and abstract model A is the attack success model, then there is no refinement relationship between model B and model A. Based on inference 1 and inference 2, we could implement the validation process in 3 steps. Step 1: check the proof obligation generated by the improved model. If the improved model is the refinement of the concrete model, the improved model is the attack unsuccess model, while the revision is unsuccessful. Step 2: if the improved model is not the refinement of the concrete model, other reasons leading to the unsuccessful refinement need to be excluded, such as manual proof is required, the proof obligation is too complicated to prove. Step 3: if other reasons are excluded, and the animation of the improved model shows that the successful attack path does not exist, then we can say the revision can defend against the original attack. The second validation method is through model checking. The Rodan platform supports model checking of the event B model to see if the various execution processes of the model can trigger all the events. So when we select Stop when all events are covered, to check the model when the result shows that the event indicating the successful attack is not covered, it means that the model has no successful attack path, and the revision in the model is effective. In this work, we proposes a formal framework for modeling a communication protocol under a given attack pattern based on Event B formalism and Rodan platform. The modeling begins from a highly abstract model corresponding to a successful attack case. The abstract model is then refined to more concrete models capturing more detailed behaviors of both the protocol and the attacker. By adding new variable attributes, the event was classified based on the access permission of the new variable. The separation rules of the model were proposed. An Event B modeling method for insecure protocols with network attacks was established. The revision of the protocol can be captured by constructing a refined version of the protocol solely. The validity of the revision can be then verified through recomposing the protocol with attack modeling and showing that the composed model is never a refinement of the original model. And, we can adopt the model checking technique supported by the Rodan platform to check if there exists an event sequence leading to the success of the attack. If the model check engine cannot find such event sequence in a setting time limit, it will give us the confidence that the revised protocol is secure under the attack. The availability of our work has been demonstrated in several case studies, and the framework can be used to validate patches and develop them. Thanks for the listening.